Hello everyone, welcome to today's presentation. I'm excited to introduce our topic, Haloalkanes and Haloarenes. In this session, we will explore the fascinating world of these important organic compounds. We'll cover their structures, properties, and significance in chemistry. Let's get started and dive into this intriguing subject. Now let's take a look at slide 2, which covers an overview of our presentation topics. We start with the introduction to haloalkanes, setting the foundation for understanding these important compounds. Then, we move into IUPAC nomming, which is essential for systematically identifying and nomming haloalkanes. Next, we explore the nature of the carbon-halogen bond, discussing its properties and how it influences reactivity. This leads us into methods of preparing haloalkanes, providing insight into how these compounds are synthesized in the lab. From there, we examine nucleophilic substitution reactions, a key mechanism through which haloalkanes undergo transformation, and we'll also look into the stereochemical aspects involved in these reactions. We'll see how HBr can be eliminated from haloalkanes, which is crucial for understanding elimination reactions. Then, we'll delve into elimination reactions more broadly, highlighting their significance. We also explore elimination or substitution pathways, comparing when each occurs and why. Moving further, we address reactions of haloarenes, including their unique reactivity compared to haloalkanes. Additionally, we will look at polyhalogen compounds, which are molecules containing multiple halogens, and their relevance. We cover common nomming conventions to help you recognize and name these compounds accurately. Finally, we'll conclude with a summary, tying all these concepts together to give you a comprehensive understanding of haloalkanes and haloarenes. Remember, each of these topics builds on the previous, forming a complete picture of halogen chemistry. Welcome to our introduction to haloalkanes. Today, we'll be exploring what these compounds are and why they are important. Haloalkanes are a class of organic compounds where a halogen atom such as fluorine, chlorine, bromine, or iodine is attached to an alkane chain. They are also commonly known as alkyl halides. Understanding haloalkanes is crucial because they have a wide range of applications, from refrigeration and anesthesia to pharmaceuticals and pesticides. Throughout this section, we'll look at their structure, properties, and how they are classified, helping us see their significance in chemistry and industry. So, let's start by diving into what makes haloalkanes unique and how they fit into the broader picture of organic chemistry. Now, let's look at the monohalogen derivatives of alkanes, which are known as alkyl halides. These compounds are interesting because their names come from the attached alkyl group combined with the halogen. Essentially, you take the alkyl group, add the name of the halogen, and that gives you the name of the compound. For example, if you have a methyl group attached to a chlorine atom, it's called chloromethane. This nomming method helps us easily identify and differentiate these compounds. Understanding how these names are constructed is fundamental as we explore their properties and reactions, which tie into the overall theme of how halogen substitution affects alkane behavior. All right, let's talk about the classification of halogen compounds. When we look at haloalkanes, we categorize them based on the number of carbon atoms attached to the carbon bearing the halogen. Starting with primary haloalkanes, these are the ones where the carbon bonded to the halogen is attached to only one other carbon. Moving to secondary haloalkanes, the carbon with the halogen is connected to two other carbons. And finally, tertiary haloalkanes have that carbon attached to three other carbons. This classification is really important because it influences the reactivity and the behavior of these compounds in chemical reactions. Understanding whether we're dealing with a primary, secondary, or tertiary haloalkane helps us predict how they'll behave in different scenarios. So, in essence, this classification is a fundamental step in studying halogen chemistry and their applications. Let's talk about IUPAC nomming. This is a crucial part of understanding organic chemistry because it gives us a standardized way to name and identify compounds. When we refer to IUPAC, we're talking about the International Union of Pure and Applied Chemistry, the organization that sets the rules for naming chemicals consistently across the world. The key idea here is clarity and universality. By following IUPAC rules, chemists everywhere can understand exactly which compound we're discussing, no matter where they are. It involves a systematic approach, first identifying the longest carbon chain, then naming functional groups, and finally assigning numbers to indicate the position of those groups. This process might seem detailed at first, but it really helps us communicate more effectively and avoid confusion. As we move forward, keep in mind that mastering IUPAC naming is essential for describing molecules accurately, especially as the structures become more complex. So, think of it as the language of chemistry that connects us all. In this context, the monohalogen derivatives of alkanes are called haloalkanes. These are simply alkanes where one hydrogen atom has been replaced by a halogen atom, such as chlorine, bromine, or iodine. When naming these compounds, it's important to specify the position of the halogen atom on the carbon chain, as well as any other substituents or alkyl groups attached. We do this by using suitable numbers, like 1, 2, or 3, to indicate their exact location. This numbering system helps ensure clear, unambiguous communication about the structure of the molecule, which is essential in IUPAC naming conventions. So, in essence, understanding how to assign these numbers correctly is key to accurately describing and differentiating haloalkanes in organic chemistry. Let's take a closer look at common naming conventions. When we talk about naming in this context, we're referring to how we label things consistently and clearly across a project or system. This is crucial because it helps us avoid confusion and ensures everyone understands what we're talking about. Consistent naming makes communication smoother and makes managing complex information much easier. For example, if we're working on a software project, using clear and uniform names for variables, functions, or modules helps everyone on the team follow along without ambiguity. It also makes future updates or troubleshooting much simpler. In the bigger picture of our presentation, understanding common naming practices is foundational. It ties into the overall goal of creating systems that are not only functional, but also maintainable and scalable over time. So, paying attention to how we name things right from the start really pays off in the long run. Now, let's take a closer look at alkyl halides and their common naming conventions. Alkyl halides are simply organic compounds where a halogen atom, like chlorine, bromine, iodine, or fluorine, is attached to an alkyl group. When it comes to naming these compounds, the process follows some straightforward rules that help ensure clarity and consistency. First, the halogen is identified and named as a prefix, such as chloro, bromo, iodo, or fluoro. Then, this prefix is combined with the name of the corresponding alkyl group. For example, if you have a methyl group attached to a chlorine atom, you get chloromethane. It's important to note that the naming conventions are designed to make it clear exactly which halogen is attached and where, especially in more complex molecules. This systematic approach is essential because it helps chemists communicate unambiguously about compounds across the world. Throughout this presentation, understanding these common naming patterns will be crucial as we explore the properties and reactions of alkyl halides. So, mastering these naming rules will serve as a foundation for everything that follows. Haloarenes are a fascinating class of aromatic compounds that are derived from benzene by replacing one or more hydrogen atoms with halogen atoms such as chlorine, bromine, iodine, or fluorine. These compounds are important in both industrial applications and organic synthesis because of their unique chemical properties. When we look at haloarenes, the key point to remember is that the halogen atom influences the reactivity and the physical properties of the compound. For example, they tend to be less reactive than benzene itself, but are still quite versatile in reactions like nucleophilic substitutions and coupling reactions. It's also worth noting that the presence of the halogen can activate or deactivate certain positions on the ring, which is critical when designing synthetic pathways. Connecting this to the overall theme, understanding haloarenes helps us appreciate how functional groups modify aromatic systems, thereby expanding the scope of organic chemistry in creating complex molecules. Let's talk about haloarenes, or aryl halides, which are a fascinating class of aromatic compounds. When naming these compounds, we start by adding the prefix halo to the name of the aromatic hydrocarbon. For example, if there's a fluorine atom attached, we call it fluoro. If it's chlorine, then chloro. Bromine becomes bromo, and iodine is iodo. This way, the name clearly indicates the presence of a halogen substituent on the aromatic ring. Now, things get a bit more interesting when we have compounds with two substituents. In such cases, we need to specify their relative positions on the ring. These positions are designated as 12, 13, and 14, which correspond to the ortho, meta, and para positions, respectively. We use these prefixes, ortho, meta, and para, to describe how the substituents are arranged relative to each other. Understanding these naming conventions helps us communicate precisely about the structure and substitution pattern of haloarenes. This is essential because the position of these substituents can significantly influence the chemical properties and reactivity of the compound. So, grasping these basics sets a solid foundation for exploring their chemistry further. Now, let's take a closer look at the nature of the CX bond. When we talk about these bonds, we're really focusing on how carbon interacts with other elements, specifically halogens, oxygen, or nitrogen. The key point here is that the nature of this bond can vary quite a bit, depending on the elements involved and their electronegativities. For example, some CX bonds are more covalent, with shared electron pairs, while others can have a more polar character, meaning there's a difference in electron density. This polarity significantly influences the physical and chemical properties of the compounds. Understanding this helps us predict reactivity, stability, and even the ways these molecules interact with other substances. So, in essence, the nature of the CX bond is fundamental to grasping the behavior of a wide range of organic and inorganic compounds, tying into the overall theme of chemical bonding and molecular interactions. Let's look at how the nature of the CX bond influences reactivity and stability. As we move from CF to CBr, we see that reactivity actually increases. This is partly because the bond enthalpy decreases as the bond length increases, making it easier for the bond to break. Now, focusing on the dipole moments, there's an interesting point here. Although we might expect the dipole moment of CF to be greater than that of CCl because fluorine is more electronegative, the actual measured dipole moment of CF turns out to be less. The reason for this is that the dipole moment depends on both the charge and the distance between the charges. In the case of CF, even though the charge is high, the bond length is shorter, which reduces the overall dipole moment. Finally, when we consider stability, it decreases as we go from CF to CBr. This is related to the increasing bond length, which weakens the bond and makes the molecule less stable overall. So, in summary, as the bond length increases from CF to CBr, reactivity increases, but stability decreases, highlighting the delicate balance between these factors in chemical bonding. Now, let's explore the methods of preparation of haloalkanes. This is a crucial part of understanding how these compounds are synthesized in the lab and in industrial processes. There are several key methods, each suitable for different starting materials and desired products. One common method involves the free radical halogenation of alkanes, where we use light to initiate the reaction and introduce a halogen atom into the molecule. Another important method is the nucleophilic substitution of alcohols, typically using hydrogen halides like HCl, HBr, or HI, which replace the hydroxyl group with a halogen. Additionally, haloalkanes can be prepared by adding halogens across double bonds in alkenes, known as electrophilic addition. Each of these methods has its own advantages and specific conditions, and understanding them helps us see how versatile and important haloalkanes are in organic synthesis. This knowledge connects directly to how we can manipulate organic molecules to achieve desired chemical transformations. Let's take a closer look at these reactions involving Ki and acids. When Ki reacts with sulfuric acid, the reaction produces potassium hydrogen sulfate and hydrogen iodide. Since sulfuric acid is an oxidizing agent, it actually oxidizes the HI formed during this process. Now, if we consider the reaction of Ki with phosphoric acid, H3PO4, it produces HI and potassium dihydrogen phosphate. This is a useful method for obtaining good yields of hydrogen iodide, especially by heating alcohols with sodium or potassium iodide in 95% phosphoric acid. It's important to note that sulfuric acid can't be used in some cases because of its oxidizing nature, which can interfere with the desired reaction pathway. Instead, thionyl chloride is often preferred because it produces gases like sulfur dioxide and hydrogen chloride, which can escape easily, making the purification simpler. Now, when it comes to the reactivity of alcohols with haloacids, tertiary alcohols are more reactive than secondary, which are more reactive than primary. The order of reactivity is 3 degrees, 2 degrees, 1 degrees. For primary and secondary alcohols, the reaction with HX, hydrogen halides, requires a catalyst, usually zinc chloride, ZnCl2, to proceed efficiently. However, tertiary alcohols react just by shaking them with concentrated HCl at room temperature. No catalyst needed. One key point to remember is that this method isn't suitable for making aryl halides, like in phenols, because the carbon-oxygen bond there has partial double bond character, making it much harder to break. So overall, these reactions and conditions are tailored based on the type of alcohol and the desired halide. However, in the presence of sunlight, halogenation takes place at the benzylic position. This is a crucial point because the sunlight provides the energy needed to initiate the reaction. The process follows a free radical mechanism, which means that radicals are key intermediates here. From hydrocarbons, this reaction specifically targets the benzylic carbon, which is the carbon directly attached to the aromatic ring. This makes sense because the benzylic position is particularly reactive under these conditions. So, to sum up, sunlight catalyzes this specific halogenation at the benzylic position through a free radical process, highlighting how light energy can influence reaction pathways in organic chemistry. The melting point is primarily determined by the strength of the lattice structure of a compound. When we look at isomeric dihalobenzenes, their boiling points are quite similar, but the melting points tell a different story. You see, para-isomers tend to have higher melting points compared to ortho and meta-isomers. This is because para-isomers form a more highly packed and compact crystal lattice. The more molecules are packed tightly in the crystal, the higher the melting point because it takes more energy to break that structure apart. Moving on to alkyl halides, the order of their boiling points is Ri greater than Rbr, which is greater than RCl, and finally Rf. As the molecules become more branched, they tend to form a spherical shape, which reduces the contact area between molecules. This weaker contact results in weaker intermolecular forces and consequently lower boiling points. Now, speaking of intermolecular forces, the strongest ones are dipole-dipole interactions and van der Waals forces. These stronger forces mean that derivatives of chlorides, bromides, and iodides generally have higher boiling points compared to hydrocarbons of similar molecular mass. When we look at physical properties more broadly, most of these compounds have a pleasant smell. The lower members of these series are usually gases, while the higher members shift to being liquids or solids. They are typically colorless in their pure state, but can develop color when exposed to air, which is an interesting transformation to keep in mind. Now, let's talk about the solubility of haloalkanes in water. They are only very slightly soluble, meaning only a small amount can dissolve. To understand why, we need to consider the energy involved. When a haloalkane tries to dissolve, energy is needed to break the attractions between its molecules and to overcome the hydrogen bonds between water molecules. Because these hydrogen bonds are quite strong, it takes a good amount of energy to break them. On the other hand, when new attractions form between the haloalkane and water molecules, they don't release as much energy because these new interactions are not as strong as the original hydrogen bonds. This imbalance means that dissolving haloalkanes in water is not very favorable, which explains their low solubility. However, haloalkanes do tend to dissolve more readily in organic solvents. This is because the intermolecular attractions that form between haloalkanes and organic solvent molecules are of similar strength to the attractions that are broken when they dissolve. So, the process is more energetically balanced, making dissolution easier. Moving on, let's consider the relationship between the structure of haloalkanes and their properties. Bromo, iodo, and polychloro derivatives of hydrocarbons are generally heavier than water. This increased molecular weight impacts their density and how they interact with other substances. And that leads us to the key idea of density and solubility. These heavier haloalkanes tend to be less soluble in water, but more compatible with other organic compounds, which is an important point when considering their applications and behaviors in different environments. Let's talk about nucleophilic substitution reactions. These are a fundamental type of reaction in organic chemistry, where a nucleophile replaces a leaving group in a molecule. The key idea here is that the nucleophile, which is an electron-rich species, attacks an electrophilic carbon, leading to the displacement of another group. There are mainly two types of mechanisms to keep in mind: SN1 and SN2. SN2 involves a one-step concerted process where the nucleophile attacks as the leaving group leaves, resulting in inversion of configuration. SN1, on the other hand, is a two-step process where the leaving group departs first, forming a carbocation intermediate, followed by nucleophile attack. Understanding the nature of the substrate, the strength of the nucleophile, and the reaction conditions helps us predict which mechanism will dominate. For example, primary substrates typically favor SN2, while tertiary substrates tend to favor SN1 due to carbocation stability. Connecting this to the overall theme, nucleophilic substitution reactions are essential for modifying molecules, building new compounds, and understanding reaction pathways in organic synthesis. They form the basis for many transformations in both research and industry. Let's discuss how halide ions behave in nucleophilic substitution reactions. The key point here is that halide ions are only substituted if the attacking nucleophile is stronger than the halide ion itself. Since halide ions are actually quite weak nucleophiles, the nucleophile attacking must be significantly stronger to displace them. This is critical because it explains why some substitutions happen more readily than others. Now, if we look at the reactivity of different alkyl halides, there's a clear order. Reactivity towards nucleophilic substitution increases as we go from Ri to RBr, then RCl, and finally RF. So, iodides are most reactive, followed by bromides, chlorides, and fluorides being the least reactive. Understanding this order helps us predict which halides are more susceptible to substitution under various conditions. It ties back to the overall theme of nucleophilic reactions. Knowing the strength of the nucleophile and the nature of the halide is crucial for predicting reaction pathways and outcomes. Here, the rate of reaction depends on the concentration of both the alkyl halide and the nucleophile. Now, when we look at the transition state from a tertiary alkyl halide, it's actually less stable because of steric hindrance, meaning the bulky groups crowd each other, making the transition state less favorable. That's why the reactivity order for SN1 reactions is primary greater than secondary, which is greater than tertiary. But for SN2 reactions, the order flips. Tertiary is more reactive than secondary, which is more reactive than primary. This difference hinges on the stability of the carbocation intermediate formed during the process. Since the tertiary carbocation is the most stable, the ionization step in SN1 reactions is easier and thus favored. In SN1, the first step is slow and is called the rate-determining step. Because the nucleophile isn't involved in this initial step, the reaction rate depends only on how much alkyl halide we have, making it a first-order reaction. So the rate equation simplifies to rate equals some constant times the concentration of Rx. Overall, understanding these differences helps us predict how different alkyl halides will behave in nucleophilic substitution reactions based on their structure and stability of intermediates. Now, let's talk about substitution reactions. These are a fundamental type of chemical reaction where one atom or group in a molecule is replaced by another atom or group. They're really common in organic chemistry and play a key role in modifying molecules to give us new compounds. In general, substitution reactions can be classified into two main types: nucleophilic substitutions and electrophilic substitutions. Nucleophilic substitutions involve a nucleophile, which is an electron-rich species, attacking an electrophilic carbon and replacing a leaving group. Electrophilic substitutions, on the other hand, typically occur with aromatic compounds, where an electrophile replaces a hydrogen atom on the aromatic ring. Understanding these mechanisms is crucial because they help us predict how different molecules will react under various conditions. They also form the basis for many synthesis strategies used in pharmaceuticals, plastics, and other materials. Overall, substitution reactions highlight how versatile and adaptable organic molecules can be, allowing chemists to tailor-make compounds for specific functions. This concept ties into the broader theme of reactivity and functional group transformations in organic chemistry. Let's take a closer look at some important substitution reactions involving organic compounds. First, we have substitution by an amino group, which leads to the formation of amines. This process is crucial because amines are fundamental in many biological and industrial applications. Next, there's substitution by a nitrite group, where the nitrite replaces a leaving group, often resulting in nitro compounds that can be further transformed. Then, we have substitution by a cyano group, creating nitriles, which are key intermediates in organic synthesis. Moving on, we see the replacement by an alkoxy group, which results in the formation of ethers through what's known as Williamson synthesis. This method is particularly important because it allows us to create ethers under mild conditions with good control. Throughout these reactions, substitution plays a vital role in modifying molecular structures, enabling us to build complex molecules from simpler ones. By understanding these substitution mechanisms, we deepen our grasp of how organic compounds can be systematically transformed, which ties back into the overall theme of functional group manipulation in organic chemistry. Let's take a closer look at the cyanide group. It's actually a hybrid of two contributing structures, which means it can act as a nucleophile in two different ways. You can think of it as C identical to N left right arrow, C equals N, where linking through the carbon atom gives us alkyl cyanides, and linking through the nitrogen atom leads to isocyanides. Now, when we consider compounds like KCN, they are predominantly ionic. This means they provide cyanide ions easily in solution. Both the carbon and nitrogen atoms have electron pairs that could potentially be donated, but in practice, the attack mainly occurs through the carbon atom. This is because the carbon-to-carbon bond is more stable than the carbon-to-nitrogen bond, making the carbon pathway more favorable. On the other hand, with silver cyanide, AgCN, the situation is different. It's primarily covalent in nature, which means nitrogen is free to donate its electron pair more readily. As a result, the main product we get from substitution with AgCN tends to be an isocyanide. So, to connect this to the larger theme, understanding whether the cyanide acts through carbon or nitrogen really influences the type of compound we form, alkyl cyanide or isocyanide, and this depends on the nature of the cyanide source. Let's take a closer look at the nitrite ion. It's an ambident nucleophile, which means it can link up in two different ways through its two possible points of attachment. One point is through the oxygen atom, resulting in alkyl nitrites. The other point is through the nitrogen atom, leading to nitroalkanes. When potassium nitrite, KNO2, dissolves, it releases nitrite ions that can bond either through oxygen or nitrogen. Since nitrogen is a better nucleophile than oxygen, KNO2 predominantly forms nitro derivatives via the nitrogen linkage. Now, on the other hand, silver nitrite, AgNO2, is a covalent compound, and it only has oxygen as a donor site. As a result, it primarily forms alkyl nitrites because it cannot link through nitrogen. This distinction is crucial because it influences how we can use these compounds in substitution reactions, especially when introducing nitro groups into molecules. The nature of the compound, ionic versus covalent, determines which linkage will dominate, affecting the final structure of the product. Let's take a closer look at the reactivity of alkyl halides. The key point here is that, regardless of the mechanism, whether SN1 or SN2, the reactivity order remains the same. I is the most reactive, followed by Br, then Cl, and F is the least reactive. This trend mainly reflects the ease with which the halide can leave the carbon, which depends on the bond strength and the stability of the leaving group. Now, for allylic and benzylic halides, they tend to be highly reactive in SN1 reactions. This is because the carbocation intermediate that forms during the process is stabilized through resonance, making these reactions much more favorable. The resonance stabilization essentially spreads out the positive charge, lowering the energy of the intermediate. To sum up, when considering the reactivity of alkyl halides towards SN1 and SN2 mechanisms, we can clearly see a consistent order. Recognizing this helps us predict how different halides will behave in various substitution reactions. Finally, shifting gears a bit, let's briefly mention substitution by a carboxyl group, which leads to the formation of esters. This is an important pathway in organic synthesis, especially in the creation of various esters used in fragrances, flavors, and pharmaceuticals. Understanding these substitution mechanisms is fundamental to mastering organic chemistry transformations. Let's take a closer look at the stereochemical aspects of nucleophilic substitution reactions. This is a fascinating area because it helps us understand how the three-dimensional arrangement of atoms influences the reaction pathways and products. When a nucleophile attacks an electrophilic carbon, the stereochemistry can be retained or inverted, depending on the mechanism involved. For example, in SN2 reactions, we typically see a backside attack that results in inversion of configuration at the chiral center. This is often called a Walden inversion, and it's a key concept because it directly impacts the stereochemistry of the final product. On the other hand, SN1 reactions tend to lead to a mixture of stereoisomers because the carbocation intermediate is planar, allowing the nucleophile to attack from either side. Understanding these stereochemical outcomes is crucial because they determine the biological activity and properties of the molecules involved. It connects to the overall theme of how structure influences function in organic chemistry. By grasping these concepts, we can predict and control the stereochemical course of reactions, which is essential in fields like pharmaceuticals and material science. Now, let's talk about certain compounds that have the fascinating ability to rotate plane polarized light. When we pass ordinary light through a nickel prism, it becomes plane polarized light, and some compounds can rotate this plane of polarization as it passes through their solutions. These compounds are known as optically active compounds. The degree to which they rotate the plane is measured using an instrument called a polarimeter. If a compound rotates the plane of polarized light clockwise, towards the right, we call it dextrorotatory, which is Greek for right rotating, and we denote this with a plus sign before the degree of rotation. Conversely, if the light rotates towards the left or anticlockwise, the compound is called levorotatory, meaning left rotating, and we mark this with a minus sign. It's important to understand that these optical activities lead to what we call optical isomers. These are compounds that have the same molecular formula, but differ in the way they interact with polarized light. This phenomenon, where the two isomers rotate light in opposite directions, is termed optical isomerism. So, in essence, optical activity helps us distinguish between different isomers based on their interaction with polarized light, which is a key concept in stereochemistry and understanding molecular behavior. Let's start by understanding objects that are non-superimposable on their mirror images, like a pair of hands. These objects are called chiral, and this property is known as chirality. Chirality is a fascinating concept because it affects how molecules interact with polarized light. When we look at stereoisomers that are mirror images but cannot be superimposed, we call them enantiomers. It's interesting to note that enantiomers have identical physical properties such as melting point, boiling point, solubility, and refractive index. The key difference lies in how they interact with plane polarized light. They rotate the plane in opposite directions. If one enantiomer is dextrorotatory, meaning it rotates light clockwise, the other will be levorotatory, rotating it counterclockwise. Now, let's talk about what makes a molecule chiral. When a carbon atom has 4 different substituents attached to it, this carbon is called an asymmetric carbon or stereocenter. The molecule containing such a carbon lacks any symmetry elements, making it asymmetric. This asymmetry is crucial because it gives rise to optical activity, the ability of the molecule to rotate polarized light. So, in summary, molecular asymmetry and chirality are fundamental to understanding how certain organic compounds behave in the world of stereochemistry. They explain why some molecules are optically active and how they relate to each other as enantiomers, connecting all these concepts to the bigger picture of molecular interactions and properties. Let's talk about what happens when we have a mixture of 2 enantiomers in equal amounts. In such a case, the optical rotations caused by each enantiomer essentially cancel each other out. So, even though each enantiomer can rotate plane polarized light, their combined effect results in 0 overall rotation. This type of mixture is called a racemic mixture or racemic modification. You'll often see racemic mixtures represented by the prefixes DL or plus, indicating the presence of both enantiomers. Now, an interesting process related to this is racemization, which is the conversion of one enantiomer into a racemic mixture. Understanding racemic mixtures is important because it highlights how stereochemistry influences optical activity and how mixtures can differ significantly from pure enantiomers. This concept ties into the overall theme of stereochemistry's role in molecular behavior and properties. Let's take a closer look at retention, inversion, and racemization, which are all fascinating aspects of stereochemistry. First, retention refers to the preservation of the original configuration of a chiral center during a chemical reaction. So, if you start with a specific stereoisomer, retention means you end up with the same stereoisomer after the reaction. On the other hand, inversion involves a complete flip of stereochemistry at the chiral center, similar to turning a glove inside out. This often occurs in nucleophilic substitution reactions, especially SN2 mechanisms. Lastly, racemization is a bit different. It involves converting a pure enantiomer into a racemic mixture, which contains equal amounts of both enantiomers. This process effectively destroys optical activity. These concepts are crucial because they influence how molecules behave, interact, and can be manipulated in synthesis and drug development. Understanding whether a reaction retains, inverts, or racemizes stereochemistry helps us predict the properties and biological activity of the resulting compounds, tying everything back to the overall theme of controlling molecular structure. When an optically pure alkyl halide undergoes ionization, it forms a carbocation that is actually planar and achural, meaning it has a symmetrical shape. This carbocation has an empty p orbital that sits perpendicular to the plane. Because of this symmetry, when a nucleophile comes into attack, it can do so from either side with equal ease. This is why the product is typically a racemic mixture, containing equal amounts of the R and S enantiomers. However, in real-world scenarios, things can be a bit different. The actual side from which the nucleophile attacks can be influenced by factors like the nature of the substrate, the solvent used, and the leaving group. These factors can make one side more favorable for attack than the other, leading to a product that is not a perfect racemic mixture. Instead, you get a mixture with unequal amounts of the 2 enantiomers, resulting in a partially optically active product. This touches on a key point about the stereochemistry of SN1 reactions. Even though the intermediate is symmetrical, the reaction conditions can steer the outcome toward one enantiomer more than the other. That's why understanding these subtle influences is crucial for controlling stereochemical outcomes in synthesis. Most of the SN2 reactions proceed with complete inversion of configuration of the substrate. This means that when the nucleophile attacks, it does so from the opposite side of the leaving group. The key idea here is that the nucleophile approaches from the back side, opposite to where the leaving group is departing. This attack causes the three other groups attached to the carbon to flip from one side to the other. This specific process is known as Walden inversion, and it results in a product that has the opposite stereochemical configuration compared to the original substrate. Understanding this inversion is crucial because it highlights how the SN2 mechanism directly influences the stereochemistry of the resulting molecule, reinforcing the connection between reaction pathways and three-dimensional structure. Now, let's move on to elimination reactions. These are a fundamental type of reaction in organic chemistry, and they play a key role in forming double bonds and other functional groups. Essentially, in an elimination reaction, a molecule loses atoms or groups, usually resulting in the formation of a new double bond. One important aspect to remember is that elimination often occurs alongside or instead of substitution, depending on the conditions and the substrate involved. The two main types are E2 and E1 reactions, which differ in their mechanisms and the conditions that favor each. Understanding these mechanisms helps us predict the products of reactions and control the outcome in synthesis. Overall, elimination reactions are crucial for transforming molecules and building more complex structures in organic chemistry. When a haloalkane that has a beta hydrogen atom is heated with an alcoholic solution of potassium hydroxide, something interesting happens. There's an elimination process where a hydrogen atom is removed from the beta carbon, and at the same time, a halogen atom is removed from the alpha carbon. This leads to the formation of an alkene, which is a key product in this reaction. Since the hydrogen atom involved in this process comes from the beta position, we call this type of elimination a beta elimination. It's an important concept because it explains how alkenes can be formed from haloalkanes under specific conditions. These elimination reactions are fundamental in organic chemistry because they help us understand how different compounds transform, especially when we're trying to synthesize alkenes. Understanding the role of the beta hydrogen and the halogen removal is crucial in predicting the products of these reactions. So, in the context of our overall theme, this reaction highlights how elimination processes are vital tools in building complex molecules and manipulating chemical structures efficiently. In dehydrohalogenation reactions, the key point to remember is that the preferred product is the alkene with the greater number of alkyl groups attached to the doubly bonded carbons. This might sound a bit technical, but it's about understanding which alkene is more stable. Generally, more alkyl groups mean more stability because of hyperconjugation and inductive effects. So, in the case of 2-bromopentane, when we perform dehydrohalogenation, the major product formed is pent-2-ene. This is a perfect example of the CBSE rule, which states that the more substituted alkene, meaning the one with more alkyl groups attached to the double-bonded carbons, is usually the major product. Recognizing this pattern helps us predict the outcome of these elimination reactions more accurately, and it's a fundamental concept that ties into the broader theme of understanding reaction mechanisms and product stability. Now, let's move on to the elimination of HBr from haloalkanes. This process is quite important because it helps us understand how these compounds can undergo transformations to form alkenes. Essentially, when haloalkanes react, they can lose a hydrogen atom and a halogen atom, here, HBr, resulting in the formation of a double bond. This is known as an elimination reaction, specifically an E2 mechanism in most cases. The key points to keep in mind are that the elimination depends on the conditions used, such as the presence of a strong base, and the structure of the haloalkane itself, which influences the ease of elimination. Also, the reaction typically results in the formation of an alkene, which is a more reactive and versatile intermediate in organic synthesis. Connecting this to our overall theme, understanding elimination reactions like this helps us see how haloalkanes can be transformed into different functional groups, broadening their application in chemical synthesis. So, which reaction occurs really depends on the conditions we have. For example, when we have hydroxide ions, O reacting with bromothane, C2H5Br, we can get different outcomes. One possibility is elimination, where a small molecule is removed from the reactant. In this case, we get C2H4 water and bromide ions. Alternatively, under different conditions, the same reactant can undergo substitution. Here, reacts with C2H5Br to produce ethanol, C2H5OH, and bromide ions. It's important to understand that elimination reactions involve removing a small molecule, in this case, HBr, from the haloalkane. This process results in the formation of a double bond, like in ethene. So, when we talk about elimination of HBr from haloalkanes, we're essentially removing hydrogen and bromine to form an alkene. Recognizing whether elimination or substitution occurs really hinges on the reaction conditions, which is a key theme in understanding organic reactions overall. Let's talk about elimination or substitution. When we're considering process improvements or problem-solving approaches, these are two key strategies. Elimination involves removing unnecessary steps or components that do not add value, streamlining the process. Substitution, on the other hand, means replacing a part of the process with a better or more efficient alternative. Both methods aim to improve efficiency and reduce waste. It's important to evaluate which approach best fits the situation. Sometimes, eliminating a step can be the quickest way to improve flow. Other times, substituting a more advanced tool or method can lead to better results without removing critical parts. These strategies are central to optimizing processes and aligning with our overall goal of continuous improvement. Always consider the impact on quality, cost, and time when deciding whether to eliminate or substitute. Now, let's talk about how alkyl halides react with sodium in dry ether. This reaction is quite interesting because it results in the formation of hydrocarbons that contain double the number of carbon atoms originally present in the halide. This process is known as the Wurtz reaction. Essentially, sodium acts as a reducing agent, helping to couple two halide molecules to form a larger hydrocarbon chain. Moving on, I want to highlight the importance of Grignard reagents in organic synthesis. They are highly reactive compounds that readily react with any source of proton, such as water, alcohols, or amines. This reactivity means that they can be converted into hydrocarbons quite easily. However, this also means that we must be very careful to avoid even traces of moisture when working with Grignard reagents, because moisture can quench their reactivity and spoil the reaction. Finally, I want to point out that reactions with metals, like sodium or magnesium, are crucial in organic chemistry for forming new carbon-carbon bonds. Understanding these reactions helps us manipulate and build complex molecules efficiently, which ties back to the overall theme of mastering organic transformations. Now, let's move on to the reactions of haloarenes. As you may recall, haloarenes are aromatic compounds where a halogen is attached to a benzene ring. Their reactions are quite interesting because the halogen influences how the ring behaves. One key point to remember is that haloarenes are less reactive than haloalkanes in nucleophilic substitution reactions, thanks to the resonance stabilization of the aromatic ring. However, under certain conditions, they can still undergo substitution reactions, especially via nucleophilic aromatic substitution. The presence of electron-withdrawing groups, like nitro groups, can activate the ring and make such reactions more feasible. Another important aspect is the role of the halogen itself. The halogen's nature, whether it's chlorine, bromine, or iodine, affects the reactivity, with iodine generally being more reactive in these processes. Overall, understanding these reactivity patterns helps us predict how haloarenes will behave in different chemical environments, which ties back to our broader discussion on aromatic compounds and their versatile chemistry. Because of the possible repulsion, it is less likely for the electron-rich nucleophile to approach electron-rich arenes. This repulsion creates a sort of barrier that makes nucleophilic attack more difficult on these aromatic rings. Moving on to haloarenes, when a phenyl cation forms due to self-ionization, it's important to note that this cation isn't stabilized by resonance. That means the SN1 mechanism, which relies on stable carbocations, is ruled out in this case. Now, regarding the instability of the phenyl cation, the key point is that the sp2 hybridized carbon in the phenyl cation has a greater S character compared to sp3 hybridized carbons, like those in haloalkanes. This increased S character means the carbon is more electronegative and can hold onto the electron pair of the C-X bond more tightly, making the cation less stable. Next, let's consider the difference in hybridization of the carbon atom in the C-X bond. In haloarenes, the carbon involved is sp2 hybridized, which influences how the bond behaves and how reactive the molecule is. Finally, in haloarenes, the electron pairs on the halogen are in conjugation with the pi electrons of the aromatic ring. This conjugation allows for resonance structures that distribute the negative charge, further stabilizing the system. Because of this resonance effect, aryl halides are much less reactive toward nucleophilic substitution. Their reduced reactivity is mainly due to the destabilization of the transition state and the difficulty in breaking the C-X bond because of the conjugation and hybridization factors we just discussed. Let's talk about how the presence of an electron-withdrawing group, specifically the nitro group, NO2, influences the reactivity of haloarenes. When this group is attached at the ortho or para positions, it actually increases the reactivity of the molecule. This is because the NO2 group pulls electron density away from the aromatic ring, making it more susceptible to nucleophilic attack. Now, moving on to the replacement by a hydroxyl group. This process involves substituting the halogen atom with a hydroxyl group, OH. Understanding how these groups influence reactivity helps us predict and control such substitution reactions. So, in summary, the key takeaway here is that electron-withdrawing groups like NO2 at specific positions can significantly enhance the reactivity of haloarenes, making them more reactive targets for further functionalization, such as replacing halogens with hydroxyl groups. This concept ties into the broader theme of how substituents influence aromatic reactivity and substitution patterns. Now, let's talk about halogen atoms and their influence on substitution reactions. Halogens, besides being slightly deactivating, actually direct substitution to specific positions on the aromatic ring. They tend to direct the incoming electrophile to the ortho and para positions relative to themselves. This is because, through resonance, the electron density is increased more at these positions compared to the meta positions. So, when a halogen is attached to the ring, it not only affects the reactivity, but also guides where new substituents are likely to attach. This pattern of directing effects is crucial in understanding how electrophilic substitution reactions proceed on aromatic rings, especially when halogens are involved. It helps us predict the products and understand the overall reactivity in aromatic substitution chemistry. Today, I want to talk about polyhalogen compounds. These are a specific group of halogenated organic compounds where multiple halogen atoms are attached to the carbon backbone. They are quite significant in various industrial applications and environmental contexts. One key point to remember is that the degree of halogenation can vary, and this influences the properties of these compounds, like their stability, reactivity, and toxicity. For example, compounds like polybrominated biphenyls or polychlorinated biphenyls are well-known examples. It's also important to note that these compounds can be quite persistent in the environment due to their stability, which raises concerns about bioaccumulation and environmental impact. Throughout this presentation, we've been exploring how different halogenations influence chemical behavior, and polyhalogen compounds are a perfect illustration of that. They demonstrate how adding multiple halogens can dramatically alter a molecule's characteristics and potential uses or risks. Today, I want to talk about dichloromethane, also known as methylene chloride. You might recognize it as a common solvent used in various applications. It serves as a paint remover, a propellant in aerosols, and also plays a role as a process solvent in the manufacture of drugs. Now, while these uses are widespread, it's important to understand the health risks associated with exposure. When levels of methylene chloride in the air rise, people can experience symptoms like dizziness and nausea. Some may also feel tingling or numbness in their fingers and toes, which indicates the nervous system is being affected. Additionally, direct skin contact with methylene chloride can cause intense burning sensations and mild redness on the skin. It's also quite hazardous to the eyes. Exposure can burn the cornea, leading to potential eye damage. Connecting this to our overall theme of chemical safety, it's clear that understanding the proper handling and potential hazards of chemicals like methylene chloride is crucial for protecting ourselves in the workplace and beyond. Now, let's talk about chloroform, also known as trichloromethane. It's been used historically as a solvent for fats, alkaloids, iodine, and other substances, making it quite versatile in various applications. Today, however, its main use is in the production of the refrigerant R22, which is a type of freon. You might find it interesting that chloroform was once widely used as a general anesthetic in surgeries. But due to safety concerns, it's been replaced by less toxic and safer options like ether. It's important to understand the health risks associated with chloroform. Breathing in about 900 parts per million of air, even for a short period, can cause symptoms like dizziness, fatigue, and headaches. This highlights why safety precautions are crucial when handling chemicals like chloroform. Overall, this substance illustrates how chemicals can have both beneficial uses and potential hazards, reinforcing the importance of responsible handling and regulation. Earlier, this compound was used as an antiseptic, but it's important to understand that its antiseptic properties actually come from the release of free iodine, not from the iodoform itself. So, the active agent responsible for its antimicrobial effects is the iodine that it liberates. However, because of its objectionable smell, it was found to be less ideal for clinical use. As a result, it has been replaced by other formulations that contain iodine, which are more pleasant to use and still effective. In essence, triiodomethane or iodoform played an important role historically, but advances in formulation have led to better options with fewer drawbacks. Today, I want to talk about tetrachloromethane, also known as carbon tetrachloride. This chemical was produced in large quantities, mainly for use in manufacturing refrigerants and propellants for aerosol cans. It's important to understand that, historically, it played a significant role in various industrial processes. However, there is some evidence suggesting that exposure to carbon tetrachloride can cause serious health issues, particularly liver cancer in humans. This highlights the importance of proper handling and safety precautions when working with or around this chemical. On a more immediate level, the most common effects of exposure include dizziness, lightheadedness, nausea, and vomiting. These symptoms serve as warning signs that the chemical is affecting your body, and they should never be ignored. Connecting this to our overall presentation theme, it's a reminder of why understanding chemical hazards and safety measures is so crucial in protecting our health and the environment. Now, let's talk about the chlorofluorocarbon compounds of methane and ethane. Collectively, these are known as freons. They are quite remarkable because they are extremely stable and unreactive, which makes them very useful in various applications. Importantly, freons are non-toxic and non-corrosive, meaning they are safe to handle and won't damage materials they come into contact with. Additionally, they are easily liquefiable gases, which simplifies their storage and transportation. One of the most common freons used in industry is Freon 12, which has the chemical formula CCl2F2. Its widespread use highlights how valuable these compounds are in everyday applications, especially in refrigeration and air conditioning. Overall, understanding freons helps us see how chemistry plays a vital role in practical, real-world technologies. Let's talk about DDT, which stands for p-dichloro-diphenyltrichloroethane. It was actually the first chlorinated organic insecticide used widely for pest control. Initially, it was seen as a miracle chemical because of its effectiveness. However, over time, many insect species developed resistance to DDT, making it less effective. Additionally, it was discovered that DDT is highly toxic to fish, which caused serious environmental concerns. Due to these issues, the use of DDT was banned in the United States in 1973. Despite the ban here, it's still used in some parts of the world. This history of DDT highlights how important it is to consider both the effectiveness and the ecological impacts of our pest control methods, tying into the broader theme of sustainable and responsible pesticide use. Thank you for joining me as we wrap up today's presentation. On this final slide, I want to highlight the key points we've discussed. First, it's important to remember that understanding the core concepts we've covered is essential for applying them effectively. We've seen how these ideas connect to broader themes like innovation, efficiency, and growth. Throughout this presentation, the main takeaway is that success often comes from integrating these principles into your daily practices. By doing so, you're not only solving immediate challenges, but also setting the stage for long-term progress. So, as you move forward, keep these concepts in mind and think about how you can incorporate them into your work. This way, you'll be better equipped to adapt and thrive in a constantly changing environment. Thank you again for your attention and engagement. And that brings us to the conclusion of our presentation. Throughout this journey, we've explored the key points that underline the importance of understanding and applying these concepts. We've seen how each element connects to the bigger picture, emphasizing the overall theme of growth and innovation. Remember, the core ideas we've discussed are not just isolated facts. They're tools you can use to make informed decisions and drive positive change. I encourage you to reflect on how these insights can be integrated into your work and everyday practices. Thank you for your attention, and I look forward to seeing how you apply what you've learned.